Welcome to PreCalc. This is lesson 2.3 continued. We're looking at the remainder theorem, which we explored in class today. We saw that if a value was a zero of the function, or if it made, actually we looked at the remainder theorem, which said that if we have a polynomial divided by x minus c, if the remainder is r, then r is really f of c. We looked at that in our exploration in class. So we're going to use that here. Instead of just plugging in values into the function, we're actually going to practice the remainder theorem for when it becomes a little more relevant. So we have example 5, the remainder theorem. Suppose 800 units of beachfront property have tenants paying $600 per week. Research indicates that for each $10 decrease in rent, 15 more units would be rented. The weekly revenue from the rentals is given by this function. It's a quadratic function, where x is the number of $10 decreases the property manager is willing to take. Find the revenue if the property manager decreases rent by $50. So normally we would just put in, well, let's look at what we'd put in. The number of $10 decreases, and they're going to decrease it by 50, so that's 5 $10 decreases. So normally we would just plug 5 into the function, but we're supposed to be practicing the remainder theorem. So if we want to know what the remainder is, right, we want to know f of 5, then we really are asking is x minus 5, what's the remainder when we try to do x minus 5 through synthetic substitution. So if I put the 5 in here, right, and evaluating 5, I want to know what the remainder is. That'll be our answer. So we have negative 150, 1,000, 480,000. Bring down the negative 150, multiply it by 5, negative 750 plus 1,000 is 250, times 5 is 1,250. Add that to 480,000 for 480,000, and we get a remainder of $481,250 because that is our remainder. That's how the remainder theorem works. Now I'm going to plug this in to show you that it does the same thing. 5 squared plus 1,000 times 5 plus 481,230. There's the same answer, 481,250. We're just practicing how the remainder theorem can be used. Sometimes it's helpful. In this particular case, it may have just been easier to plug 5 into the equation. Another example of this, the number of tickets sold during the Walled Lake Northern football game can be modeled by this cubic equation, where x is the number of games played. Find the number of tickets sold during the 12th game of the season. So they want to know when x equals 12, or if we're looking at the polynomial function, if x minus 12 is a factor. It probably won't be because we're anticipating a remainder. So we're going to plug 12 into for synthetic substitution. In this case, it might be more efficient to do this if you don't have a graphing calculator. The numbers should work out pretty nicely. 1 times 12 is 12, 0. 48 times 12, that one might not be as fun. 576, add that to 74. 650 is the remainder. So x minus 12 is not a factor of this polynomial function, which is good for the football team. This means they brought in a revenue of $650 for this problem. All right, so that's our remainder theorem. If it's divided by x minus c, or we're doing synthetic substitution, that means x equals c. Plug that into synthetic substitution, whatever your remainder is, that's equal to the value of f of c. Our factor theorem, I kind of hinted at that where I said x minus 12 is not a factor of this polynomial. Polynomial f of x has a factor x minus c if and only if that f of c is 0. So in other words, if and only if our remainder if we're looking at tying this to the remainder theorem, if our remainder is 0, then what we were checking for the factor would be a factor as long as the remainder is 0. Synthetic division and remainders. If r is the remainder obtained after synthetic division of f of x by a factor x minus c, then the following statements are true. R is the value of f of c. If r equals 0, then x minus c is a factor of the polynomial. If r equals 0, the remainder, then c comma 0 is an x-intercept of the graph. And if r equals 0, then x equals c is the solution of f of x. We're going to be determining if these factors that are given are factors using synthetic division. If they are, we're supposed to use the polynomials or the binomials that we pulled out and then write a final answer in factored form using all of the factors. So some of you might not be able to split this cubic function up right now and factor it, but if we can find out if x minus 5, therefore x equals 5, is a factor or not using synthetic division, then we can factor from there. I have no missing terms, so I don't have to put any zeros. 1 times 5 is 5. Negative 18 plus 5 is negative 13. 5 times negative 13 is negative 65. Plus 60 is negative 5. Times 5 is negative 25. Hey, how about that? We lucked out. This one was a factor. So right now in factored form, x minus 5 is one of the factors. I don't want to just write this down, though. It's a quadratic x squared minus 13x minus 5. If it can also be reduced. Problem is, there are no factors of x and negative 5 that will work. I'd have to solve it using the quadratic formula. So we're going to do that right now. We have the opposite of b over 2a. The b squared minus 4 times a times c is 189, square root of 189. 189, I believe, it's not a prime number. Oh, wait, 63 is divisible by 9. So 189 is divisible by 9, 21 times. So this would be 13 halves plus or minus 3 square roots of 21 over 2. In terms of factors, since x equals that, one of these factors will be x minus 13 halves plus 3 square roots of 21 over 2. And the other factor would be x plus, or no, still minus 13 halves minus 3 square roots of 21 over 2. Not really going to factor because these are irrational roots. This is the only rational root. Didn't say to write all rational factors, though it said to write all factors. And our next problem, I'm going to test x minus 5 again and hope it works, but if it doesn't, then I'll try the x plus 2. So when I do the minus 5, that means x equals 5 is going to be tested. 1, negative 2, negative 13, negative 10. No missing terms. 1 times 5, 3 times 5, 2 times 5. How about that? That worked out. We're happy. So we have x minus 5 as one of our factors, x squared plus 3x plus 2 as the other factor, and what's nice is this one is factorable, x plus 2 by x plus 1. So we bring those factors down. All of them were rational in this case. Our last example of this, here are two factors given. Should have given you one that didn't work so that we could try it, but it's nice when it does work out right away. X equals negative 2. We're going to check this to see if x plus 2 is a factor. So I have 4, negative 9, negative 19, 30. Again, no missing terms from the polynomial that were the dividend. Bring down our 4. This is negative 8, negative 17, positive 34, 15, negative 30. Once again, we're lucky that that one worked out. So one of our factors is x plus 2. We have to figure out the other factors from our 4x squared minus 17x plus 15. I'm going to try, guess, and check. I If that doesn't work, well, you know what? I'm going to first see if it is even factorable. 17 squared minus 4 times a times c is 49, which is a perfect square, so this one is factorable. Or I could just finish the quadratic formula. I'm going to try 2x and 2x. I don't know that that's going to work. 5 and 3 would give me 15, but 3 would give me 18, so that's not going to work. So maybe I do try 4 and 1. And if I do 5, that's 20 and 3. So negative 20 and positive 3 does add to negative 17. So our other factors are 4x plus 3 and x minus 5. We now have we've completely factored this polynomial by determining which one of these were a factor, putting that as one of the factors, and then factoring the remaining quadratic. In the first example, it was not factorable, so we did do the quadratic formula to find the irrational factors. That's a little frustrating. You're going to subtract 13 halves from both sides, then subtract this value for one of them and add it for the other one, so you still get all of your factors. This concludes the video notes for lesson 2.3, using the remainder theorem to evaluate functions, and using the factor theorem and remainder theorem to find a factor and then continue factoring to break it down. Have a great day.